All right, so the next talk of the afternoon is given by Deeparnab Chakrabarty on graph connectivity and single element recovery via linear and OR queries.
Okay, thanks everyone, and thanks for inviting me. It's been a great workshop. So I want to talk about, so the title of our paper with Safar Asadi from Rutgers and Sanjeev Khanna from Penn is graph connectivity and single element recovery via linear and OR queries. So there are a bunch of results in the paper, but I'm going to sort of focus on one of them. And it's this rather natural sounding problem. So there's an unknown non-negative non-zero vector x. Okay, so it's n-dimensional, capital N dimensions. And the only access you have, the measurement you have, is you can take a subset of 1 to capital N, you'll get the sum. And the goal is to just recover one coordinate in the support. Okay, so you just want to get j, not even xj. You want to get one coordinate in the support. And the question is, how many queries do you put? Okay, so the answer is 2 words. You can do binary search. So you can query the first half. Okay, and if the sum is non-zero, you know that there is something in the support, so you recurse on that. If the sum is 0, then you can recurse on the right. So this is going to work in log n queries. And in fact, you don't even need the sum. You only need the fact whether the sum of the entries is 0 or non-zero. So these are called OR queries. Maybe I'll not talk about OR queries anymore. It's a much weaker notion. It works. Furthermore, it's easy to see that you need log n queries, right? There are 2 to the n vectors, and you get the n bits of information, and you only get sorry. So yeah, you can just have the singleton like EI, the vectors with exactly 1, 1, and there are log n bits of information. You get only 1 bit per query. So the point is that this algorithm, binary search, is highly adaptive. And this proceeds in log n rounds. You ask a question, then you ask a question again. So the question we want to know is, if I give you fewer rounds, like 2 rounds of queries, how many queries do you need, right? So, yes. The entries are non-negative, yeah, non-negative and real. Good. So, so if you have fewer rounds, then you do what is called shallow binary search. For example, if you have only 2 rounds, here's what you can do. You break the vector into root n chunks, and you ask for the sums of each of these chunks, that root n queries. One of the chunks is going to be positive, and then you just focus on that in your second round, every singleton, and you find at least 1 element in the support. Okay, so it's R rounds. This takes n to the 1 by R rounds per queries, and at R equal to log n, it's 1 round per query for log n. So the question is, so maybe the takeaway from this talk is that this is actually tight. You cannot do anything better. And maybe I hope to get to some open questions, but if not, maybe the main open question is, prove the same thing when the vector is actually 0, 1 vector. So the vector is a real vector, or a real non-negative vector. I think that it's true for 0, 1 vectors, but we don't know, and we'll come to that. So that's the open question. Hopefully come to that. Okay, so that's the thing that I would like to talk to you about a little bit, but let me sort of put it in perspective of where this arises. So we sort of got into this question on looking at queries on graphs, in particular cut queries on graphs. So suppose you have an unknown graph on n vertices, small n vertices, and you should think of this as actually an unknown vector in n choose 2 dimensions. And I should point it's a multi-graph, so maybe between 2 vertices you can have many edges, right? So you can it's a weighted vector, this x vector, and you could think that you have linear measurements on this vector. So you have a n choose 2 dimensional vector, and you can get the dot product of q dot x. So if that is too much, just think about, you can take a subset of vertices, and you get to know how many edges cross this subset. These are called cut queries. And this way of looking at unknown graphs has been studied extensively, and mostly people have focused on reconstruction of graphs. How many queries do you need to reconstruct the graph? And there's a whole line of paper. But suppose you don't want to reconstruct the graph, but you just want to figure out some properties of the graph. So in particular, if you want to just know if the graph is connected, or you want to find the spanning forest in this graph, then how many queries do you need? You don't need to reconstruct the whole graph. And the question that this paper looks at is, what is the round versus query trade-offs? Like non-adaptively, how many queries do you need? If 2 rounds, how many queries do you need? And so on and so forth. And how is it connected to the single element recovery problem? Well, from a single vertex perspective, right, that vertex perspective, there is a small n-1 dimensional vector, which sort of the vector's ith coordinate basically says how many edges it has to be vertex I, right? So that's a single element. That's an unknown vector from a vertices perspective, and a single element recovery is finding one single edge from that vertex, right? And if you want to figure out the spanning forest, it's the least thing you need to solve. From every vertex, you need to find at least one edge coming out of it. So this problem, single element recovery, is sort of, I think, integrally connected to this connectivity question of finding the spanning forest question in a graph. Okay, so let me at this point say something which is crucial. So our work and this talk is going to be focused on deterministic algorithms, right? So you want to, there's no room for error. And the reason is that if we go to randomized, the landscape is pretty well understood. So for the single element recovery problem, in fact, in one round, you can get a random sample in polylog n entries, right, using L0 samplers. And furthermore, and this is this work of Anguha McGregor, that you can actually get in a graph, you can get the spanning forest in polylog O tilde n queries, right? So these in fact even cut queries, you can make this work go through. So if you allow randomization, there is no the trade-off. You can do most things non-adaptively. So the focus of this talk is what's the story in deterministic algorithms, and maybe the takeaway is that if for deterministic algorithms there is a trade-off. You cannot do much with non-adaptive algorithms, and the things probably go smoothly as the number of round grows. Okay. So again, so this kind of question is connected to various other fields. So I'm not going to go over this, but maybe I'll say something where I was interested in. I was interested in submodular function minimization, still interested in it, and graph cuts is one particular example, and this sort of led us to this cut queries, which led us to this sort of problem, this simple single element recovery problem. So I'm not going to talk too much in the interest of time. I'm wanting to give you a flavor of the result. So here are the main results of this paper. So first is what I promised, that any R-round deterministic algorithm to recover this single element in the support, the shallow binary search is the best. So any algorithm must make at least n to the 1 by r minus 1 in some round. And this is when I say even with linear queries. So what I mean is that instead of getting the sum of the entries, you can actually get a linear, you can ask for a linear vector and get the dot product. Even in the stronger model, you have this lower bound. And the other result, main result in the paper is that so the first one is a lower bound, the second one is an upper bound, which says that in any graph, there is a deterministic order R round algorithm. So maybe it's 36R in the paper, which can be improved, which makes n to the 1 plus 1 by r queries and finds the spanning forest of this graph. Okay, so that's an upper bound. And again, here I mentioned that this algorithm actually uses a weaker, it just needs the OR query. So given a subset of given a two subset of vertices, is there an edge between them or not? So sort of bipartite independent set queries. Okay, so that's all the main results. I'm going to focus on the first one. So again, sort of to remind, the problem is there's an unknown vector. I'm having some queries. I want to find a single coordinate. And in R rounds, you need to make at least n to the 1 by r minus 1. Okay, so that's the main result. And the heart of the matter is actually a non-adaptive question, right? So which is the sort of we call the support trapping question. So here's a slightly different problem. So I again have this unknown vector. The algorithm needs to make one round of queries, with small q queries. But its objective is to just return a subset which traps the support. It has to return a subset such that at least one of the entry in the support is non-zero, right? Or alternately, the sum of the xi's in that subset is non-zero. So that's the goal. And now what we need to show is that for this problem, both the number of queries and the size of the subset, so small q and small s, both of them cannot be small. In particular, if both of them were suppose much smaller than square root n, then there is a two round, much smaller than square root n query algorithm, right? Because I'll do this one round algorithm and I'll find this smallest support and then I'll just do singleton queries on all of them. So if the lower bound of 2 round square root and lower bound were true, then it better be that it cannot, that for this one round non-adaptive question of support trapping, both Q and S cannot be small. I cannot make small number of queries and trap something in a small region. This is the necessary condition for a lower bound. So I'm going to show this thing. And this is the heart, because once you prove this, the proof for the R round thing is an inductive application of the support trapping question. So this is sort of, this support trapping question is the heart. So any questions so far? So this is the, yeah.
Usually like can't be both less than, right?
Right. So yeah, can't be. So actually Q times S has to be less than N. That's what we'll prove.
The product can't be less than N.
Yeah, that's what we'll prove. Both of them cannot be small. Was there another question? No. Okay. Good. So so how does one prove this? So it's an adversary argument, right? So let's think about what is a one round Q query algorithm. Well, the queries are all prefixed. So it's a matrix. It's a Q cross N matrix, which is called capital A. And what do we want as an adversary to prove this lower bound? So we want to say that given this matrix capital A, we want to give answers to these queries. So we want to find this answer small a. So we want to give this answer vector. And what is the property that we want? Well, we want that after getting these answers, the algorithm should not be able to say, aha, here's a small set where I'm going to trap the support. Which means for any subset S, which is small enough, so any subset S of size small s, there should be some vector X, which the algorithm can then give, which will say, look, there is nothing in the support here. But this, it cannot be any arbitrary vector. It has to be consistent with the answers. So what we want is for any subset S, there better be a vector X such that it's consistent. So the AX is equal to small a. So the answers are the same for those queries. But on that subset, the vector is 0. Or in other words, since it's non-negative, the sum of the entries is 0. So I want to say that this vector will fool that subset. So I'm using here crucially that the algorithm is deterministic, has to be correct and for every for every answer it gives, and this is sort of crucial. So it means that for any subset, if I can find this X, this algorithm is foiled. Okay, so that's an adversary argument. Now, if you just look at this, you'll say, yeah, sure, the 0 vector will always. So X has to be non-zero. So we're going to add this extra row, which will pin down X to be non-negative. So we're going to say that there is like a 0th round query, which is the all ones, which is asking for the sum of the Xi's. And that has to be non-zero. And by scaling, we'll just assume that it is equal to 1. So that's like the first row. So the problem at hand is basically this. We want, given such a matrix A, and with this extra row maybe, we want to return a small a vector. That's our goal as an adversary. So that for any subset S, we can find an X, which is consistent, but at S is equal to 0. So that's what we prove. But I'm going to sort of use this remaining 15 minutes to show why Q times S is equal to N, or that thing shows up. And it's much easier to appreciate it if we assume a little more. We'll assume that X actually can now have negative entries as well. Okay, it's cheating in the sense the proof, our final proof is quite different, but it's going to give you the indication of why Q times S equal to N comes out. Okay, so this is the goal of the adversary. We're going to make the adversary's life slightly easier by saying that this greater than or equal to 0, I'm going to remove it. So this is a simpler case for the adversary. We want to prove that given at this matrix A, I want to find this answer small a, so that for any subset of small size, I can now give a real vector, which could be negative, which is consistent. It sums up to 1, but on X it sums up to 0. Okay, good. So let's go through this. How do you prove this? So we'll make 3 simple observations. So first observation is that if one of the queries is small, right? If one of the rows of this matrix has less than S non-zero entries, the answer better be 0. Otherwise, the adversary has found this subset, right? The particular subset that it is queried, it is going to return that. So for every small rows, the particular value of small a should be 0. So that's observation 1. Observation 2 is actually saying what the algorithm should not do. It should not have something which is a linear combination of the other rows. It's just foolish because the answers will just be linear combination of the other things. So some row in the span of 1 and the other rows of A, it can be removed. That query was a useless query. And now the third thing is the sort of the, maybe the main definition. We call a subset, so we have a queries and we say a subset S is safe if 1S, so the support of, so once the S coordinates in 0 everywhere, 1S is not in the span of the other queries, okay? For the adversary, it is safe. Why? Well, if that is the case, if 1S is not in the span, then we can always find an X which has a solution to these equations, right? So again, this is going to say that X is non-negative, this is consistency, and I add an extra thing which is not in the span of these things, so this will have a solution. And that's precisely what we wanted. We wanted to find an answer which, you know, fools the adversary at the given set S. So what's the worry? The worry is that maybe, you know, there is a set which is not safe. So to show that this is not the case when Q and S are both small, here's the what the adversary tries. So I'm given this matrix A, and it's going to get to a different set of vectors V with Q plus 1 vectors, such that the all ones will always be there. The all ones is always there in this vector space. And all the original queries in the row are in the span of this vector space. So I don't lose information of those things. So these are the two things I need. And the third thing I need is, so it's a mouthful, so let's go on. For any small subset, either 1S is not in the span, so S is safe, in which case the adversary, if the algorithm returns this, the adversary can cheat it. Or 1S is in the span of the small things in the V. So what is small? Small entries of in this vector space, the vector is small if the rows have only S non-zero elements. So why is this a good thing? Because when something has only less than S non-zero elements, observation 1 says my answer has to be 0. So if something is in the span, if some query is in the span of other queries where I'm always giving 0 answers, it will only thing the adversary will know, algorithm will know that the answer to this is also 0, which means that the algorithm cannot be returning this set S. So that's, if we can get this set, this collection of vectors, then we have proved this thing. So this is, I think, what we are going to, I'm going to repeat this. So if I have this set of vectors V which satisfies these conditions, what we are going to do is the first query, all ones we have to answer 1. For all the queries which are small, I'm going to answer 0. And for everything, all the other big queries which has more than small s ones, I can answer whatever I want. Okay, that's going to be this answer vector A prime. This is not the answer to the original queries. This is the answer to these queries. But since every original query is in the span of these vectors, I can get the answers to the original queries by taking the similar combination of these A prime things. Okay. So just to sort of make sure, from the set of queries capital A, we're going to get this matrix. And once we get this matrix, we're going to get this vector A prime, which is 1 for the top one, 0 for the smalls, and for big, it's a don't care. You give whatever you want. And then, since everything is in the span of these, this A prime will give me the final answers to the queries or algorithms query. This is what I'm going to return. And the fact that all the small things is either 1s is either not in the span, in which case it's safe, or it's in the span, in which case x is equal to 0. It will basically mean that if I get my hands on this vector space and I get this A prime from which I get this A, that is the answer that will foil the adversary. No matter what set the algorithm gives, I can always return x where that on that S it is equal to 0. Okay, so why should such a vector space exist, and where does Q and S come in? So again, this is what we want. We want all ones to be in the vector space. I'm never going to throw all ones out. All the original queries are in the span, and for any small set, 1s is not in the span. Okay, sorry. So I'll describe this how to get this V procedurally. We start off with all the queries that the algorithm gives. So initially, this matrix is the capital A matrix. So 1 is clearly there, all original queries are there. And then I ask whether there is a subset S which is safe. Okay, so maybe not. Maybe there is a small subset S such that 1S is in the span of the vectors, but it is not in the span of the small vectors, which means that it is a span of, it is using 1 and maybe some big vector. So the claim is that if that is the case, if 1S is in the span but not in the span of just these small things, it must be using some big vector as well. What does that mean? It cannot be that this 1S is just the span of the small vectors and the all ones vector. Okay, that's the claim. Okay. So this claim is also easy to see, but let's come to that later. Why does this claim, what was this claim going to allow? The claim will allow us to do the following. So this set S has been given and it is making us unhappy. So 1S is in the span, but not in the span of this. But then I find this big vector which is involved in expressing 1S as a linear combination of this. So I'm going to change my vector space by kicking that big vector out and bringing this 1S back in. And now 1S is a small vector. So I've decreased the number of big vectors and increased the number of small vectors. So this can happen at most Q times, because after Q times, maybe all the vectors were big and they're all kicked out. And now I have only small vectors, in which case I'm done, because if there are no big vectors, I'm happy. Good. So why is this that a small vector cannot be the linear combination of just the ones and just the smalls? And that's where this Q and S will come in, right? So suppose there is a small vector, which can be, it is in the span of V, but it does not include any big vector. Well, then it can be written as a linear combination of small, at most Q small vectors, because the size of V is Q, and maybe this one vector, which is all ones. Well, that means that all ones can be written as a linear combination of Q plus 1 many small vectors. But that means that at the very least, the support of like each of these small vectors has S locations that are Q plus 1. So Q plus 1 times S has to be greater than N. So if Q times S is much, much smaller, then this is not possible. So that's how you get basically the fact lower bound on Q times S. And just to say, for larger number of rounds, you'll basically have Q1 times Q2 times up to QR will be bigger than N. The same kind of idea applied inductively. Yes. Sorry, sir, can you repeat that?
Do you ever use the condition you're working with 2 rounds, or you're just, because I think the analysis you never used it.
So the question is, did I ever use 2 rounds? So this is just a 1 round problem, which is in 1 round, I want to trap the thing in the support. And if that 1 round question was not true, then I would get a faster 2 round algorithm. So I'm ruling out a lower bound to a lower bound for a 2 round algorithm. Sorry, I confused you more. So this lower bound is for the trapping problem, which is basically a 1 round question, which asks Q questions and has to trap it in a size of S. It does not prove a 2 round immediately, but I'm saying that this is the heart, and you can inductively apply and get a 2 round and K round algorithm. Good. So, okay, I have 5 minutes. So let's go back. So this is a thing that X could now have negative entries because it's a field now. So, but X is not allowed to be negative. So what goes wrong, right? So again, this is the goal again. We are given this matrix. We have to produce this vector A such that for any subset S, this system has a feasible solution. Okay. So I must have that X should be at least non-negative. So what goes wrong in the previous argument? So the 3 observations, these 2 observations are fine, but the problem is that this notion of safe is no longer true, right? As in, if a set of S, if it is not in the span, so this thing has a solution, but it may not have a solution with all the X's being non-negative. So this sort of clean way of the linear algebraic argument breaks down. Okay, but the reason of this root n, the Q times S being at least n, that is something that carries forward. So in the remaining 2 minutes, I just have 1 slide on it. I'm going to show you how do you take care of these, this X greater than or equal to 0. So this is not true with X greater than or equal to 0. So what do you need to do more? So let's fix a subset S. Okay. So again, what is the goal? We want to produce an answer vector A so that for any subset S, I can fool that subset. So fix a subset S. There are many such subsets. Let's fix a subset S and let's see what do we want. Well, we want precisely this. We want to find an X which satisfies this system of linear inequalities. So with this makes it inequality, which means I want to find an A so that this sort of system of linear inequalities has a feasible solution. So this polytope is non-empty. So I want to find an A. So this is a parameterized polytope, parameterized by A. I want to find an A so that this is non-empty. So you use Farkas Lemma to figure out what are the possible A's. Okay, so it's not at all important to see what this looks like right now, but it is some sort of system of linear equations. So this is some other object which is parameterized by capital S, this S that I have fixed. And if you look at it, it will say that this answer A that I'm trying to find for this particular set must lie in some polytope ds. So for a fixed S, to fool that set, I have to give an answer in this set ds. But I want to fool all the sets. So I want to basically find an answer A, which is in the intersection of all DSS when I index over all small sets. Okay. So we want to prove that this intersection, which is just a huge system of linear equations, is non-empty. How do we prove something is non-empty? We apply Farkas Lemma again and prove that that system does not have any valid solutions. And this is the part which I'm not going to go to here, and I also run out of time. It is there to prove that that system has no equations is where the support thing argument again comes up. We basically prove that if that were not non-empty, the dual of this, then the all ones vector can again be written as a convex combination, actually dominated by a convex combination of q many small vectors. And again, the same reason of q times s, if it is smaller than n, it will not hold, comes up. So the reason for the root n is just the product thing, but the journey is slightly different. Okay, so that's all I wanted to say. So let me end with two open questions. And I think they're doable open questions. I should put that. So one is what I mentioned, that this whole method really uses the fact that x is a real vector. Okay, this won't work for 0, 1 vectors. So can one prove that you can get for R rounds n to the 1 by how did that happen? Sorry. Yeah, so can we prove that for Boolean vectors? So I want to say that you cannot hope to get a tight result like n to the 1 by R, because actually algorithmically you can shave off log factors below. Okay, so you can actually do better than shallow binary search with some queries. So that's something, if you don't know, that's very interesting, but maybe you cannot do better than any polylog and shavings. And in fact, there is work by Amit Chakrabarty and his student Manuel, and I think Manuel is here in the audience, which shows that this is actually true if the computation is done over a ring zk for some constant k. So if you're getting answers mod k for some constant k, even when the vector is 0, 1, then such a thing is true. And I think they also could prove it for r equal to 2. But the methods are very different, as in the methods are combinatorial, and I think Manuel will be a better person to answer them. So, but the general thing is still open. And the next question, this is relating back to the graph. So we did prove, so again, the single element recovery was motivated from the graph connectivity question. But we are not able to lift it to the whole thing. So this thing is still open. Like if you want to find the spanning forest using linear queries, using some queries or cut queries even in R rounds, deterministically, is it true that you need to make n to the 1 plus 1 by R lower bound? So that's like a direct sum version of this question. And we were not able to lift for the inequalities thing. If the queries are OR, which is much weaker, then actually this is true, and it's also there in our paper. Okay, I think I've gone over time, but thank you again for your attention.
All right, thanks a lot for the talk. Any question before? Yeah.
So for the fact that you're getting this lower bound only for real x, not for 0, 1 x, does that imply that your graph lower bounds are for multigraphs rather than?
So our graph lower bound, we don't have a graph lower bound. That's the open question. But the open question, even for multigraphs, that will be great. I think for normal graphs, you have to solve open question 1 first. But for OR queries, it does not really matter because you're only getting 0 or 1. So, and those are for any graph.
Right. Any other question?
Thank you. So have you thought about the case that you have a cost function associated to the queries, for example, based on the size of the query?
The answer to this question is not, maybe no, we've not thought about it. But so you're saying to make a bigger queries, you have to pay more.
Have to pay more, but not linear anymore,
No,
sublinear.
that's an interesting question. Yeah. We can talk offline, not about this problem, but in some other things we have thought about.
Any other question? Right. How about let's thank Deeparnab again.